Okay, hello everyone. Welcome to another episode of Science and Technology Q&A for kids and others. And we have a bunch of questions saved up that I didn't get to on other sessions. And let's see, where should we start? Question here from, looks like TS. Can I talk about turbulence and why it's the greatest unsolved problem of classical mechanics, or at least it might be taken to be that way. Okay, so let's talk about turbulence. What is turbulence? Sort of its full name is fluid turbulence. Here's the basic story. Let's say that you have a stream of water and you put your finger in the stream of water. The water will flow around your finger. And the question is, what will the water do as it flows around your finger? Clearly, the water has to, kind of part around, going around your finger, and then has to kind of rearrange itself when it comes back behind your finger. If the water is flowing slowly, it will show what's called laminar flow, kind of flow in layers, where essentially the water comes in towards your finger, or let's imagine it's a slightly larger object, towards some cylinder. You put it down into the water. And the water kind of flows smoothly around that cylinder. The water, as it comes in towards the cylinder, it kind of parts, goes around the cylinder, reforms behind the cylinder. And you'll see pictures. If you put, for example, ink in the water, you'll see the streamlines of where the water goes as the ink is in the water and it's being carried with the water. You'll see it kind of smoothly stream around the cylinder. So that's what happens if the flow of the water is slow. If the flow of the water gets faster, several things start to happen. What will happen at first is behind the cylinder, there will be, well, first thing you'll see is that behind the cylinder, there'll be a couple of eddies that form. On the two sides of the cylinder, there'll be eddies where the water is kind of swirling around behind the cylinder, two little eddies behind the cylinder. Same thing if you put a plate in water, you'll see that around the two ends of the plate, there'll be two little eddies that swirl around. As you make the flow of the water faster, it will start breaking off. And the eddies break off in what's called a vortex street, where first the eddy at the top will break off, then the eddy at the bottom will break off. And you'll see behind the plate or the cylinder, you'll see this kind of these kind of offset eddies just streaming back in the water behind the plate or the cylinder. So that's the next thing that happens. So what happens when you make the water go even faster? Well, the eddies will start to break off, not in the original vortex street. They'll be kind of like, lampposts on opposite sides of the street. There'll be just a periodic array of vortices. When you make the flow faster, the vortices will start breaking off, not periodically like that, and there'll be a clump of two vortices, and then there'll be nothing, then there'll be another clump of vortices, and so on. And you'll start seeing interactions between the vortices in the vortex street. As behind the cylinder, these vortices will start interacting with each other. Okay, then what happens, as you increase the rate of flow of the water even further, you'll start getting something much more random behind the plate. The water will seem to be just sort of flowing around randomly. You'll make this wake behind the cylinder and it'll look quite random. That's turbulence. And the phenomenon that you see, and it's a very generic phenomenon in fluids, when sort of rates of flow are slow, you get this kind of laminar, smoothly sliding type behavior. When rates of flow are high, you get this random turbulence forming. Okay, there's a lot to say about this. And a fundamental question is, why do you get that kind of randomness in fluids? I've been interested in this question for a long time. I think I kind of know the answers now, and the answers are quite interesting. So first thing to talk about a little bit is about patterns of flow in fluids. So the question is, if you have a fluid like water, and you have an object of a certain size, and you have a speed of flow of a certain amount, and then you have a much bigger object and a different rate of flow, how do the patterns of flow compare depending on the size of the object, the rate of flow, the viscosity of the fluid, that is the as you kind of put pressure on the fluid, how much will the fluid then flow? That's essentially the viscosity. If you have something like syrup has a much higher viscosity. It has a much greater tendency to resist motion in the fluid. The kind of characteristic form of viscosity is if you take two plates and you put fluid in between them and you try and start moving one of the plates, how much force does it take to move that plate? If the fluid is very unviscous, if the fluid is like some light kind of oil or something, the viscosity is low, it takes very little force to start sliding one plate on top of the other. If the fluid is something like syrup that's very goopy, then it takes a lot of force, and that means that the fluid has high viscosity. So there are these different parameters. There's the rate of flow, there's the size of the object, there's the viscosity of the fluid, there's also the density of the fluid, how much mass the fluid has per unit volume. So those are 4 parameters. And those are the parameters that determine kind of the pattern of flow in a fluid. Now, it turns out that in the end, you're going to say this is that you can characterize the flow by just a number. So what you have to do is you have to form a number out of these parameters. So out of something which has dimensions of velocity, something with dimensions of length, something with dimensions of viscosity, and dimensions of density. And it turns out that there is a single combination of those things that involves is the object that is a dimensionless object. It's just a number. So I think it's called the Reynolds number. And let me think, how do I work this out? I think it is, that's right, it's length times velocity divided by viscosity times density, I think. Maybe the viscosity and density appear differently. Let's see, I could probably work that out. I think viscosity has dimensions of mass, length to -1, time to -1. So that probably means, okay, so that means that the density has to be, that's right, it must be length times velocity divided by viscosity over density. So, okay, what does this formula mean? This is a dimensionless number that characterizes the pattern of flow you'll get. So notice that it has length times velocity. So if the thing you're looking at is bigger, the fluid flow is a certain velocity, you can sort of trade off. You can have a smaller thing, but faster fluid flow, and you'll get the same pattern of flow so long as the product length times velocity is kept the same. So what one can do then is to characterize these different kinds of flow in terms of the value of the Reynolds number. So I mentioned that, for example, at very low flow rates, I said, but what I really should have said is low Reynolds numbers, the flow is laminar. So a low Reynolds number might be a Reynolds number of 1/10 or something, 0.1. When the length times the velocity divided by these other things is less than 1/10, you'll just see nice smooth flow. As the Reynolds number gets up to be, I don't know, 1 or so, you'll start seeing those eddies formed behind the object. By the time the Reynolds number is like 10, you'll start seeing vortex streets and so on. You'll have a nicely developed vortex street. By the time the Reynolds number is 100 or so, you'll start to get more randomness and turbulence. What's the Reynolds number for a typical kind of thing? The Reynolds number for an airplane flying through the air is about 10 million. The Reynolds number for a car driving is maybe 1,000, I'm not sure. The Reynolds number for you just running your finger through water might be of order 1. So there are these different kinds of things that go at different speeds in different fluids. Air has a much lower viscosity than water, for example. But in the end, the thing that sort of tells you what kind of flow will you get is this number that is this combination of parameters, the Reynolds number. Okay, so the basic sort of fact of fluid mechanics is that low Reynolds number, you get smooth laminar flow. At higher Reynolds numbers, you get turbulence. And as the Reynolds number goes up and up and up, all you see is more and more turbulence, more and more kind of randomness in the flow. So when you have a waterfall or something, that's a very turbulent flow that's at a high Reynolds number. There is actually one other number that characterizes fluid flows, which is the Mach number. well, there are actually several others if you include other effects, but if you're just dealing with a fluid and you're not dealing with the temperature of the fluid and things like this, the one other parameter is the Mach number. The Mach number is the ratio of the speed of the fluid to the speed of sound in the fluid. So for example, for air, the speed of sound is around 330 meters per second. That's in standard sort of sea level and so on. That's about 600 and something miles per hour. And what characterizes when you look at flow past an object, if the flow is if the object is moving at a very small fraction of the speed of sound, then the Reynolds number is all you need to know what the flow is going to look like. If it goes close to the speed of sound or even above the speed of sound, the Mach number is important. As you get to higher Mach numbers, you go above the speed of sound, you start seeing shock fronts be formed and things like that. But that's irrelevant for thinking about things like turbulence. Turbulence is a story of flow below the speed of sound. I mean, it happens. Turbulence also happens above the speed of sound, although it works differently. But turbulence is a phenomenon that happens where the transition to turbulence happens at Reynolds numbers of around maybe 100 or something. Okay, so what is turbulence? Well, what happens in fluid flow? So when you have a fluid, what's happening is the fluid has some momentum. The pieces of the fluid, well, okay, we can look at it at the level of the molecules from which the fluid is made. If you looked in a powerful enough microscope in water or something, you just see a bunch of molecules bouncing around. What happens in the actual flow of water is that all those molecules sort of randomly bounce around, and the net result is that a little packet of fluid, for example, will have some average speed going in some direction, will have some average velocity. So then what happens is you have a little region of fluid that has some average velocity. It's tending to move in this direction. That means that fluid has some momentum. It has some, it will tend to keep going in that direction. The thing that prevents it from going is viscosity. Viscosity is like the analog of friction for a liquid or a fluid. It's the thing that takes motion and kind of damps it out and just turns it into heat. When you are dealing with solids, for example, you try and push something over the ground, and you're pushing it, and there is a force of friction that tends to push against you pushing the object. And what's happening is the energy that you're putting in to push that object that isn't succeeding in pushing the object, that energy is being dissipated as heat associated with friction of the object. And it's the same thing with fluids. When there's motion in a fluid, that motion will be dissipated as a result not of friction, but of viscosity, and that motion will eventually turn into heat. So what that means is you are pushing on this piece of fluid, and for a while, that whole region of fluid will move, but eventually viscosity will kind of damp out that motion, will stop that piece of fluid moving, and will turn that collective motion of lots of molecules into the individual motions of individual molecules, which we view as being heat. The random motion of these molecules is heat. So viscosity damps out large-scale motions of a fluid. So and turns what was large-scale motion of molecules into the small-scale motion that is heat. So one thing that happens in a fluid is there's conservation momentum, but then there's damping of motion as a result of viscosity. So there are really these two different kinds of things going on in a fluid. There are sort of things that having to do with momentum and keeping momentum, and things having to do with the frictional forces, the damping of momentum. So those have usually two names: the inertial process of sort of associated with inertia, with the tendency of a fluid that's moving to just keep on moving. That's sort of inertial effects. The other is dissipative effects, taking the motion of the fluid and dissipating it into heat. So a lot of the story of fluid mechanics is a competition between these two phenomena of inertial effects and dissipative effects. In fact, the Reynolds number, this thing I told you characterizes the kind of type of flow, is essentially a ratio of the sort of amount of inertial stuff going on in a fluid divided by the amount of dissipative stuff going on in a fluid. So what that's telling you is when the Reynolds number is higher, when the inertial stuff is more important, the sort of motions of the fluid all around, are important compared to the effect of damping out motion. And that's when the motions are important, that's when the motion can get wild and turbulent. Okay, so in a fluid, there are some kinds of motions that kind of survive longer than others. For example, eddies, vortices, are one of the types of motion in a fluid that tends to survive. So what is a vortex? A vortex is just a fluid going around in a circle. And that's what happens in a hurricane, for example, is a giant example of a fluid vortex. And what tends to happen is that the processes of viscosity and so on that damp out motion, they have a much harder time getting rid of that circular motion than they do getting rid of linear motion. It is a consequence of essentially topology. It's like it's as if the fluid is kind of winding itself around the center. It's winding itself around the eye of the hurricane. And that motion, it's very hard to continuously deform the motion of the fluid from something that's winding itself around this kind of hole in the middle to something which is just not moving at all. Whereas if you have linear motion, it's much easier to just slow down the linear motion and the linear motion disappears. When you have this kind of circular motion that has this sort of topological hole in the middle type thing, it's harder to dissipate that. And so vortices tend to be a kind of long surviving feature of fluid motion. In general, one can think of the structure of a fluid in turbulence, for example, when the fluid is doing very complicated things. If you look at it on a small scale, you'll see a whole bunch of these little eddies of fluid just going around little eddies. Okay, so in turbulence, one of the big effects is a thing called the eddy cascade. And what happens is, roughly in turbulent flow, you'll have a sort of the big motion of the fluid, the fluid is going around this obstacle, that sort of creates a big eddy as the thing that's sort of an eddy that's the size of the obstacle. It turns out to be a feature of fluid flow, not completely well understood from first principles, but it's an empirical fact about fluid flow that big eddies turn into smaller eddies. And so what starts as a big eddy eventually grinds up into smaller and smaller eddies. And eventually those eddies get so small that, okay, so you can compute the effective Reynolds number for an eddy, which depends on essentially the size of the eddy, the characteristic length of the eddy. When the eddies get small enough, eventually viscosity starts taking over and the eddy is dissipated. But so the story of a lot of turbulence is a big eddy is produced by the large scale sort of constraint on the flow, like you're going to flow around this obstacle. And then that eddy, that sort of large scale eddy gets broken up in a cascade of smaller and smaller and smaller scale eddies. Okay, that cascade is often called the Kolmogorov cascade after a Russian mathematician named Andrei Kolmogorov, who did lots of interesting things, particularly around sort of the application of statistical ideas to other kinds of fields like information theory and like physics. So this cascade of big eddies turns into smaller eddies, as I say, this is primarily an empirical observation. An important fact about that eddy cascade is that same kind of dimensional analysis of just saying what units appear in what formulas and so on actually tells you that the cascade of eddies has a very definite form. It's k to the minus 5/3. If k is essentially the size of an eddy, the chance of having an eddy of a certain size falls off according to a power law like that. And there are many power laws that show up in many places. Fractals are kind of a characteristic sort of pattern of thing that you see when you have those kinds of power laws that relate to geometrical objects. And that sort of gives you a characterization of kind of what it looks like if you look inside a fluid. It's kind of a little bit like a random fractal where there is this power law distribution of sizes of eddies. So anyway, the sort of the overall picture of empirical fluid mechanics is this, when you're going to get turbulence, you get a big eddy, it gets ground up into smaller and smaller eddies. The positions of all those eddies are kind of random. And eventually when the eddies get small enough, they get dissipated into heat and the turbulence isn't there anymore. But so this idea that sort of eddies break down into smaller eddies, that tends to be true in an ordinary fluid in 3 dimensions. In 2 dimensions, it's probably not true. In 2 dimensions, actually, kind of the opposite may happen. In 2 dimensions, it may be that a small eddy can actually build up into larger eddies. And in fact, that's what probably happens in things like the Great Red Spot at Jupiter, because the atmosphere of Jupiter is, well, this is a little bit unconvincing, but it is roughly, it exists in a thin layer. Like the atmosphere of the Earth is a thin layer on top of the Earth. But in Jupiter, maybe one can think of it as being sort of thin layers of fluid. And so what's happening is that something like the red spot is forming from lots of eddies coming together to form this big eddy that has lasted for a few hundred years. It's a giant storm. It's a giant hurricane-like storm in the atmosphere of Jupiter that, you know, was seen by Galileo and is still seen by us today, but probably won't be seen for forevermore, so to speak. It will eventually be dissipated, just like hurricanes on the Earth are dissipated, just like fluid vortices everywhere get dissipated by viscous processes. But the tendency to go sort of the tendency to break a big eddy into smaller eddies seems to be a feature of three-dimensional fluids, and it sort of goes more or less the opposite way in two-dimensional fluids, maybe. I say maybe it's a slightly complicated story, and pieces of it are not well understood. I remember there's a lot of things one can do with soap films where one is seeing some of the effects of the development of turbulence in a soap film. It's a very sort of two-dimensional thing. It's very, very thin soap film. And you can see nice effects when you see, for example, when you see the sort of all the Newton's fringes of all of these in a thin soap film. You'll see all these nice colors that come because of the interference of light in between the two sides of the soap film, and you can kind of see the motion of the soap fluid in those patterns of in those interference patterns. And that allows you to see some fluid motion in soap films rather nicely. And for example, the description that I gave of flow around an obstacle producing this vortex street and so on, you absolutely see that in 2 dimensions. But the way that those things build up into sort of larger scale structures and produce turbulence is a bit different. Okay, so anyway, that's the sort of empirical story of fluid turbulence. And when you look at things, okay, so for example, when people talk about aeroplanes and, you know, fasten your seatbelts, we may be heading into some turbulence. What does that mean? Well, on the surface of the Earth, the atmosphere of the Earth it's a fluid, and there's motion in the fluid. That motion is what we normally call wind, and some of the time the wind will be flowing very smoothly over parts of the Earth. Sometimes the wind will produce turbulent flow in the atmosphere of the Earth. So, for example, behind a mountain, as the air flows over the mountain, you might get sort of turbulence behind the mountain. As in the atmosphere of the Earth, as you get different heating and cooling of the air, that will produce motion in the air. That's something not included in the most basic kind of fluid mechanics. This idea of heating and cooling of fluids is sort of a next level of fluid mechanics, but that's what causes a bunch of large scale motion in the Earth's atmosphere. And you'll see different kinds of motion associated with that. So for example, and there's also motion associated with the rotation of the Earth, has forces on fluids in the Earth's atmosphere, and that produces other kinds of motion. So when you talk about turbulence for airplanes, the kind that there's, for example, with a cloud is where it is because that's where the water vapor that's where there is sort of the upswelling of air coming below the cloud that's pushing the sort of the cloud up, and kind of the force that's pushing the cloud down is in equilibrium. And you basically have these winds effectively below clouds. For example, for thunderclouds, you have very strong winds, and there are very strong winds that basically pull air from the bottom of a thundercloud up to the top of the thundercloud. So if you like fly a small plane, it's like very bad idea to go to the base of a thundercloud, because your plane can get pulled up in the interior of the thundercloud up to 50,000 feet or something through the core of the thundercloud, because there's this very strong wind that blows upwards inside that. But so there's one kind of flow of sort of rapid fluid flow that happens around clouds, particularly I think cumulus clouds, and that rapid flow can lead to turbulence. There's also what's called clear air turbulence, which is the more common kind that people are like, fasten your seatbelts, the plane is going to be bumping around, but you couldn't tell that it's going to be bumping around because there wasn't any cloud in sight. That can happen, for example, the jet stream that is at certain latitudes, that's a kind of characteristic wind that is as a result of the rotation of the Earth, and that can produce this kind of turbulence. So in general, when an airplane is kind of bumping through turbulence, you can ask, how big are the bumps? Well, this Kolmogorov cascade that I mentioned to you, this k to the minus 5/3 law, that actually tells you how big the bumps are. And I don't know completely how accurate that is, but I think it's a decent model. And so what that basically tells you is there's a much higher probability for a smaller bump than there is for a bigger bump. And that means, for example, when you try and design an airplane, you say, how strong do the wings have to be? Is it possible that there'll be a giant eddy where the plane will just drop 300 feet? Because there's effectively, there's almost a vacuum in the atmosphere at that point. Well, that's unbelievably unlikely because of the structure of this Kolmogorov cascade. I think airplanes can drop like 100 feet or something, and their wings are set up so that they'll still be just fine. They'll kind of flap a bit, but otherwise be fine. And that's kind of an estimate that you give based on these rules about how turbulence works. By the way, I might mention that for an ocean surface, it's a little bit different. It's not quite the same dynamics as motion in the bulk in air. There's a thing, I think it's called the Pearson-Moskowitz spectrum, which is another kind of power law thing that describes kind of the height of waves. So when you're trying to work out, you have when you have when you're designing your boat and you're saying, I want to make sure that it has big enough, hulls and things that it's not going to that it's not going to, or it has enough stabilization that it's not going to make everybody seasick. You say up to, what's the probability that you get waves of this height and so on, and that's given by that spectrum, and that's a similar kind of thing to this cascade for fluid turbulence. Okay, so anyway, that's a little bit of the empirical story of fluid turbulence, and the fact that you'll get these this kind of cascade of eddies and things like that. Okay, so now we can ask a more fundamental question, which is, how can we explain why is there this randomness in fluid flow? It's a question I've been interested in for a long time. So there are some theories about this. I think I know what the answer is in the end, but let me explain a little bit about the theories of this. So when you describe a fluid, there are some equations, partial differential equations, called the Navier-Stokes equations, developed in the early 1800s, that are a description of how the fluid will flow. So those equations tell you, they say they have dv by dt, where v is the velocity, t is the time. They're talking about the rate of change of velocity is proportional to something that has to do with it has a term v dot grad v, which is a term that is associated with, if you look at the change of a velocity with position and how that compares to velocity itself, that's another piece of those equations. There's a piece that involves the viscosity and technically Laplacian of the velocity field, which is essentially giving you kind of that's associated with viscous damping. So anyway, there's this equation. It's basically got 4 terms if you include pressure in the equation, and it's a nasty equation. It's an equation that's really hard to solve. So when you try and solve it algebraically, there are a very small number of solutions that people know. So for example, a very early success of that equation was, if you have a sphere and you're dropping the sphere through a fluid, the question is, how much drag is there on the sphere? And there's a thing that's usually called Stokes's formula. And when the fluid flow is slow, it has low Reynolds number. There's a very nice 6 pi eta AV, I think. Eta is the viscosity. I think the formula is just has a little 6 pi in it, and it has the viscosity and it has the radius of the sphere and the velocity, and that tells you, that simple algebraic formula gives you the kind of the drag on the sphere, the amount of force that the fluid will push back as the sphere tries to move through it. That works at low Reynolds numbers. As the Reynolds numbers increase, then that formula has a much more complicated form. And it's only known at the point where you're just starting to develop those eddies behind the sphere that I mentioned earlier. There's still a formula that's known, but it's pretty complicated. And as the flow gets more complicated, nobody has any idea what that is like, and there probably isn't a standard formula written down in terms of standard mathematical functions for what happens. And what happens is complicated. But you can think of it as, oh, we've got these equations. Gosh, that tells us everything about how fluids work. Let's just solve the equations, then we'll know everything. So then a big question will be, if we're just solving the equations, can it be the case that the solutions to these equations involve all this random stuff that is characteristic of turbulence? Can those equations support apparently random solutions? Nobody really knows. It's complicated. Okay, so there are a few things that are known. So for low Reynolds numbers, you can, for very, very low Reynolds numbers, you can find nice solutions to these equations. Okay, so a couple of things to say. So when you look at these equations and you ask a question like, let's say we had a solution to these equations and we make a small change, a small perturbation in the fluid. We just change the fluid velocity a tiny bit. How much effect will that have on the solution to the equations? So that's in a sense, how stable or unstable is the fluid flow? If we kind of put our finger in the flow and yeah, you know, there's a little effect from our finger, but nothing big, and the flow eventually has exactly the same form as it had before, that's a kind of stable version of the flow. If we put our finger in the flow and putting our finger there just changes everything, that's an unstable flow. Okay, so is fluid flow stable or unstable? At low Reynolds number, it's stable. At low Reynolds number, you put your finger in there, the effect of your finger will be only quite local, and the fluid velocity will be damped out. The effect you've had will be damped out by viscosity. You'll kind of see no sign of your finger as you flow, as the fluid flow progresses. At high Reynolds number, the story is potentially different. Can we figure out what the story is? Okay, so in 1963, I think, Ed Lorenz did the following thing. He was interested in flow in the Earth's atmosphere. What he did was he took the Navier-Stokes equations, these fancy differential equations that represent fluid flow, and he made what's mathematically called a modal truncation of these equations. What he effectively did was he said, let's just think of these equations in terms of a small number of eddies. Let's just imagine that these equations are, that the solutions to the equations are just described in terms of roughly, let's say, 3 eddies. I'm eliding a bunch of stuff. These are actually Fourier modes, and that's not quite the same as decomposition in eddies, but it doesn't really matter. Basically, it's saying, let's assume that the fluid flow is governed by these particular forms. Okay, so then you got much simpler equations, now called the Lorentz equations. And he said, well, let's try solving these equations. These equations are now ordinary differential equations that's somewhat simpler to deal with. And what he found is that a small change of the initial conditions to those equations, so if you just change the initial velocity just a tiny bit, you can have a very large effect on the later velocity that the equations will imply. So what that suggests, that turned into kind of people talking about the butterfly effect, so to speak. If a butterfly flaps its wings, that's a small perturbation on a fluid. In Lorentz's equations, a small flapping of the wings, a small change of velocity, could have a big effect later on in the solution to the equations and describing the velocities. Okay, so in fact, that phenomenon of a small change can have a big effect is something that had been thought about, been known about actually since the mid-1800s in different forms, but there are different places where that's important. So for example, I'll give you another example. Let's say you have 2 spheres, 2 balls, and you bounce the 2 balls against each other. Okay, they bounce. Let's say the balls are exactly aligned on axis. then when they bounce, the two pieces that bounce are just flat against each other, and the balls will just bounce back the way they came. But let's imagine that the balls hit a tiny, tiny bit off center. They hit a little bit off center, then the ball the ball will bounce. They'll bounce further. They won't come back directly the way they came. They'll bounce at some angle. If you make these balls bounce again, and they've kind of moved a bit off center, then the next time around, they'll hit even further off center. And so they'll bounce even further off center. So what will happen is every time the balls kind of go back and forth, they will be they'll let's say double the distance off center that they hit each other. You can do the same thing with light. If you have a mirror that's a convex mirror, and you have kind of light bouncing back and forth between, let's say, convex mirrors, the thing, if the light hits right on axis of these two convex mirrors, great, it'll bounce back and forth. But as soon as it's off axis, it'll get sort of exponentially more off axis. It might double the amount off axis that it is every time it goes back and forth. And so that's a kind of amplification phenomenon, that a small change in the initial conditions, a small change in where the light was originally bouncing, whether it's just a tiny, tiny bit off axis, will have a large change in the overall motion. So that phenomenon got called sort of the chaos phenomenon, sensitive dependence on initial conditions. The phenomenon happens even in pretty simple mathematical systems. Let me give you an example. So let's say that you just take a number, call it x, and you double it. Okay, but let's say you don't consider the actual doubled number, you just take the fractional part of the number. So let's say I have the number, 1.7 or something, or 0.7, I double it. I'm going to get 1.4 when I double it, but I'm only going to keep the fractional part. So I'm only going to keep the 0.4. Okay, actually, let me make this simpler. Let me just say I multiply it by 10 every time instead of doubling it. So I multiply by 10 every time this number. So that means I start off with, let's say, 0.45. At the next step, I multiply by 10, so that becomes 4.5, but I only keep the 0.5 then. So 0.45 turns into 0.5. Let's say the original number I had was 0.12345. Okay, that'd be the initial number. I multiply it by 10, I get 1.2345, but I cut off the 1, I keep only the fractional part, so I get 0.2345. I do the same thing again, I get 0.345, etc. So effectively what I'm doing is, every time I multiply by 10 and take the fractional part, I'm like excavating another digit down in the number, okay? So let's say I'm trying to figure out what's gonna happen after 1,000 steps. Well, I will have excavated to the 1,000th digit in this number. So if I want to know what's going to happen, if I say this is a process, I'm thinking about it as something like light bouncing back and forth that could be modeled with something very much like this, is often called an iterated map. And this iterated map is just you apply the same function over and over again, and the function is multiply by 10 and take the fractional part. So what that function will succeed in doing is taking the sequence of digits that was whatever number you gave initially, and at every step it'll excavate another digit. It'll put to the front the next level digit in this number. So if you say, well, I want to know what happens after 1,000 steps, you've got to know 1,000 digits of that number. So that means that if you wanted to predict, if you have a system, it's light waves, it's something else, you want to predict what the system does after 1,000 steps, you have to know incredibly accurately what the initial condition was, what the initial number was, the initial position of the light ray, or whatever it was in order to know what will happen after that amount of time. And that is the essence of the sensory dependence on initial conditions phenomenon, this chaos phenomenon, chaos theory phenomenon. And that's the effect that Ed Lorentz found in Lorentz equations back in 1963 or so, that in this simplification of the equations of fluid flow, just a small change in the initial conditions would be amplified in exactly this way that I described of excavating digits, could be amplified and would just keep on getting amplified. That was what his model said. Okay, so that led people to say, oh my gosh, the reason there's randomness in fluid flow is because we're excavating these initial digits. We're excavating, we have this initial velocity of the fluid. And since we don't know it exactly, we sort of can assume it's kind of random. And then the reason the flow is random is because we're excavating all the digits of the initial conditions. This is actually a very weird theory, because it's basically saying that, well, first of all, when we're excavating digits like that, we're saying, what is the precise velocity of the fluid to 1,000 digits of precision? Well, it's pretty meaningless, because by the time we're at 1,000 digits of precision, we're at a tiny fraction of the size of a molecule of the fluid. And in fact, when we want to get that precise about a fluid, we have to be microscoping down to look at individual molecules. So in a sense, what one's saying when one says, if one says that the effect, that the behavior of the fluid depends on these very, very detailed features of the initial conditions, one's saying it's not good enough to just know the kind of mathematical description of the fluid velocity. You actually have to dig all the way down to the molecules and see at the level of the sort of 1,000th digit of precision what's going on. So that means that these equations that describe fluid flow aren't actually valid. We have to actually know about the molecules to be able to describe that. So that's one possible thing that might happen in fluid dynamics, is that the effect of just individual things happening at the level of molecules are being amplified. And maybe one theory is that the reason we see randomness in fluid flow, in turbulence, is that we are essentially seeing an amplified version of the randomness of all those little molecules bouncing around at a microscopic level in the fluid. That is a possible theory. That is kind of the chaos theory idea about where the randomness in fluid turbulence comes from. I think this idea is not correct. Basically, what happens in a real fluid is that most small perturbations are damped by viscosity. That's what viscosity does. How come Ed Lorentz didn't see that? Well, because the simplification he made of the Navier-Stokes equations does not include viscosity. It includes only, it kind of only sort of backs into including a little bit of the effect of viscosity. If you do the same thing he did, but you keep more terms, more eddies effectively, you stop seeing the effect. It's so in a real fluid, most of the time, I think you will not see this effect of sensitive dependence on initial conditions in that way. Now, it can be the case that the fluid is kind of on a knife edge. The fluid could either flow this way or flow that way, and it's very sensitive which way it will flow. In that very rare circumstance, the butterfly that comes along and flaps in one direction or the other might tip the fluid from going this way to going that way. But I think that's an incredibly rare phenomenon. I think the most generic thing is that most butterflies, I'm sorry, butterflies, don't have a huge effect on the future history of the world. That is, they, it's not the case that most, most things about fluids are determined by those microscopic things. Now, having said that, there is another effect. There are some other pieces to this that relate to weather forecasting and that have to do with how accurately you need to know the kind of velocity of the fluids to be able to accurately forecast the weather for some amount of time. There is an effect that's sort of related to this chaos theory thing that limits, that is the thing that limits the time that you can make weather forecasting predictions for, and so on. But I think that's the more important effect in turbulence is a quite different effect. The more important effect is that something that I kind of, really, I suppose, discovered, although there were precursors of it that were known but not really recognized for a long time beforehand, that I kind of discovered in the early 1980s, is that when you're dealing with programs, it's very common for even a very simple program that you say, this is a simple program, it's just going to do simple things. But that program, when you actually run it, will do very complicated things. In fact, it will often do things that look completely random. When, if you really to analyze it, you'd say, oh, it's all made by the program. But when you just look at the thing it produced, it's like, oh, that just looks random. So a typical example from mathematics of the same phenomenon is the digits of pi. There's a way to compute the digits of pi. You can know that they're the ratio of the circumference to diameter of a circle, but there's a mathematical procedure for generating those digits. Yet once you generate the 3.1415926, etc., that sequence of digits looks, for all practical purposes, random. Now, they're not random because of sensitive dependence on any initial conditions. They're random because of this phenomenon that simple programs, simple processes can generate apparently random things. That's related to this phenomenon of computational irreducibility that I've spent lots of time investigating. It's a very core feature of what happens in sort of the computational universe of programs. I think it's the main thing that happens in fluid turbulence too. I think that what's actually happening in fluid turbulence is that these Navier-Stokes equations, when you kind of, what they're doing is the equivalent of computing digits of pi. So they're doing things where just by running those equations, you are essentially intrinsically generating something which is complicated enough that it seems random to us. And I think that's where the randomness in turbulence comes from. One feature of that claim is that it suggests that, okay, so if the randomness of turbulence came from amplification of molecular motions, then if you run the same experiment twice, you won't get the same pattern of turbulent flow, because the second time you run it, you won't have the exact same configuration of molecules and so on. So the experiment won't be repeatable. You'll get a different pattern of flow. On the other hand, if what's happening is that it's effectively the flow process is computing digits of something like pi, it's not exactly the digits of pi, it'll be some other kind of computation, but it's just doing a computation whose result happens to look random, then it can be the case that running it a second time, you might get the same result. So you might ask what actually happens in practice. And I've long been curious about this. And in fact, there are experiments done in liquid helium, very well-controlled experiments about fluid flow, which appear to show long time, like multi-hour, complicated patterns of flow that are repeatable between different runs of the experiment. However, as of at least 20, or what was it, 25 years ago or something now, when I talked to people who studied these things, they were like, well, we've seen this. If you really ask us, we have seen this. We don't understand it. It's so weird, we don't think we can publish it because people would make fun of us because it's just so weird. I think in truth, it's actually a core part of what's going on in fluid turbulence is this kind of essentially computational process that is repeatable, not always precisely repeatable because there'll be differences that are sort of hard to reproduce in the actual configuration of the fluid when you set it up, but that sort of computational process is the core of what's happening in fluid turbulence. And that idea has a lot of consequences. So for example, if you want to use a fluid to do a computation, that suggests you might be able to do it. You might be able to just set up the initial conditions for the fluid and just say, okay, fluid, do your thing. And the result will be that the fluid will compute something that is that might be the thing that you usefully wanted to compute, but you're using the fact that the fluid can do a computation. That is also the reason that it can produce apparent randomness. You're using it for some purpose that you want. So that's an example of something you could do as a result of that. But what's happened, so I mean, sort of the bigger picture, I would say, in fluid turbulence, it remains a bit of a mystery why fluids show apparent randomness in their flow. I think the answer is it's from this sort of intrinsic computational process, but that's not it's not been fully nailed down. Now, one thing people ask is, for example, there's this $1 million prize that got put up, the Clay Millennium Prize, one of a collection, but one of them is for showing what the existence and uniqueness of the Navier-Stokes equations. So what does that mean? So the Navier-Stokes equations, as I mentioned, are these equations that describe flow of a fluid. And the question is, if you've solved those equations, do they actually have a unique answer? In other words, if you set up, it could be the case that you say, I want to solve these equations. I've got this particular set of initial fluid velocities, and I'm going to then figure out what will be the result of that fluid flow. And it could be the case that the equations stick their tongue out back at you and say, sorry, can't give you a unique answer to that. That's one possibility. The other possibility is that the equations could say, what that initial configuration that you put in causes a fluid velocity that goes to infinity. That happens in, for example, the Einstein equations for general relativity, for the structure of space-time, you can get these singularities that form. We don't know if similar singularities can form in the fluid equations. So what that would mean is you've got these fluid equations and you're saying, okay, I set up this configuration of fluid flows, and somehow the fluid will pile itself up in some weird way, and pretty soon there'll be a piece of fluid that's going at infinite velocity. Very weird, very embarrassing. We don't know whether that can happen according to the equations of fluid flow. It would be kind of a sign that the equations of fluid flow aren't the whole story of a fluid, because, well, actual fluids don't have infinite velocity, don't have infinite density, things like that. You might also ask, given these fluid equations, what happens if you just solve them on a computer? Well, on a computer, when you're outside the domain where you can do kind of analytical algebraic solutions, what you have to do is something where you're taking this fluid, this description of a fluid in terms of this continuous velocity field, where you say there's a certain velocity at every position in the fluid, and you're breaking it down. You're saying, actually, I want to just break that into little pieces, where I say there's a little packet of fluid that has this velocity, another packet that has this. You might use finite element methods, and you might say you're breaking this fluid down into all these little finite elements that are kind of like sort of little triangles of fluid that all sort of mesh together with other triangles and so on. And then what you do is then you've turned the solving of this fluid equation, which is a continuous calculus type equation, into something that involves like all these discrete pieces and seeing how they fit together. Well, needless to say, that's an approximation. You're not solving the original precise continuous calculus-like equations. You're solving this numerical approximation. And there's a question of, does that numerical approximation work? And in particular, when you see turbulence, are you seeing randomness in the fluid or in your computational fluid? Are you seeing randomness because something went wrong with your scheme, or are you seeing randomness because there's some intrinsic randomness in the equations? It's really hard to tell which of those you're seeing. Now, actually, sometime in the 1980s, I developed a method for studying fluid mechanics, which instead of going from the fluid equations down into this sort of discretized thing that you can deal with on a computer, I said, let's look at something that is an idealization of the molecules from which the fluid is made and go up from the molecules. So I had a cellular automaton model of these molecules in which there's just a grid of possible positions for the molecules, and there are discrete molecules, and they can go at discrete velocities and so on. And what happens is, as a result of essentially the phenomena of thermodynamics, it doesn't matter it's a fundamental fact that the details of the molecules that make up a fluid do not affect the equations of fluid flow, other than in the parameters like viscosity. So the Navier-Stokes equations, their form of those equations is the same for air and for water. The viscosity is different, the density is different, but the form of the equations is the same. And so my idea was, take the molecules and make them incredibly idealized and simple, and you'll still get the same sort of large-scale form for the fluid equations. And that works rather nicely. And there are many technical details and all sorts of mathematical complexity to the whole thing. But basically, you can go up from sort of the underlying, some idealization of the underlying molecules. Now, when you make that underlying idealization, you can have something where, one of the issues when that whole thing that I mentioned about sensory dependence on initial conditions is a phenomenon of picking real numbers, picking numbers that can have any number of digits. You can then, knowing precise numbers is very hard, because numbers can have infinite variations as you look at all these digits. If you're looking at a cellular automaton where you just have these discrete objects, there is no such issue. It's either a 1 or a 0, more or less. It could be a 0.7258464, et cetera, et cetera, et cetera. So you don't have any of those issues. So you can much more precisely ask questions like, given an initial configuration, is it the case that can you go from some simple configuration of molecules to, for example, a more complicated configuration? Yes, that will often happen. And could you go from a configuration of molecules that represents a fairly simple pattern, represents the flow of the fluid and potentially shows you the emergence of sort of apparent randomness at the level of the fluid flow, and how does that relate to the randomness of the individual molecules? So I studied this a bit in the 1980s, and yes, indeed, it seems to be the case that the randomness that you get in fluid flow is a kind of computational randomness of the kind that I mentioned, related to digits of pi, not a sensitive dependence on initial conditions kind of randomness. And you can kind of tell that in this scheme for doing fluid mechanics. It's hard to tell from the equations themselves. You have to just do math and calculus and things to work on the equations. If you're doing the thing I mentioned, you can use a computer to kind of simulate what happens with the equations. So there are many, many questions about fluid turbulence, very interesting questions. I mean, a question of sort of how much computation can fluid turbulence do, that relates to questions about, is it decidable? Is there, if you say, I want to precisely know what happens in this fluid flow, maybe there is no finite computation, no computation that a computer can do in anything less than infinite time that will answer the question of what happens in this fluid flow. That seems to be a likely possibility. And that's sort of almost inevitable if sort of fluid dynamics and fluid turbulence can do computation. In some sense, you might say that the existence of fluid turbulence is a sign that fluids do serious computation. If they didn't, then the flow would tend to look simple and we'd be able to say the answer is going to be this. But actually the flow looks really complicated, and that's kind of a sign that to know what the flow is going to be, we have to do a bunch of computation. And we could say, and then the fluid itself is doing computation. And so in a sense, we could say, and I hadn't really thought of it this way, but we could say that the existence of fluid turbulence is an in-your-face sign that phenomena like fluid dynamics show computational sophistication, that there is the possibility of sophisticated computation going on even in a fluid flow. And there are many, many examples of fluid flows. I mean, another one is splashes. They're a good example of somewhat repeatable patterns of flow, et cetera, et cetera, et cetera. Anyway, fluid flow is a great area, an example of a lot of kinds of issues that come up in physics. You know, one of the things that was always sort of a disappointment about to me was that for a long time, physicists didn't really talk about fluid flow. People had said, well, we tried to analyze fluid flow and didn't really work very well. So let's leave it to the engineers to actually build things that, you know, that flow through fluids, and the physicists will kind of ignore it. And the problem of turbulence was one of these things that there was sort of an obscure footnote saying, oh, well, there's this problem of turbulence. And then you go on with the physics textbook and talk about what you can compute. And that was a piece you couldn't compute. But I think it's sort of a core thing that is a sign of kind of, it's a flag that physics was waving at us that said, yes, there's sophisticated computation going on in physical systems. And for the most part, physics kind of ran away from that idea. All right, that's it's a long discussion of fluid turbulence. Thank you for that question. Oh my. Did I yak on for a whole hour about fluid turbulence? Well, it's a great subject. All right, let's see. As a comment from Prutz here, how about intelligent fluids that are about to take over the world? Yeah, well, this is one of the issues about identifying intelligence and so on. You know, the fluid motion in the atmosphere is a complicated, sophisticated computation, just like the motion of the little electric currents in our brains are complicated, sophisticated computations. And it's kind of like this aphorism, you know, the weather has a mind of its own. Do those motions of the fluid in the atmosphere, in the Earth's atmosphere, how do they compare to the kinds of computations that happen in our brains? One of the things that has come out of science that I've done is this thing called the principle of computational equivalence, which kind of suggests that at a raw level of computation, they're really equivalent. The you know, the kind of the motion of fluids in the atmosphere and the kind of the electrical activity in our brains, these are computationally equivalent. So in some sense, if we say, well, gosh, you know, the future of the world hangs in the balance of the behavior of the atmosphere, then in a sense we're saying, yes, it is true that that alien intelligence of the weather, which has a mind of its own, sort of is taking over in some sense. I mean, it's a kind of it relates to this question of, you know, yes, it can be some sort of abstract intelligence. It just doesn't happen to be human-like intelligence, even though it might be computationally just as sophisticated as the things that are going on in our brains. Well, let's see. There are questions here. Let me try and just do a couple of others. Let's see if I can find some shorter ones here. Ah, boy. Question from Jack. Which self-driving technology is better, imaging or LIDAR? Oh, I don't know, but I can at least describe what that story is about. So you got a car. It's trying to figure out, it's driving along. It's trying to figure out what's in front of it. Is it safe for it to drive in this direction? Is it safe for it to change lanes? Things like that. It has to know what's there. We humans know what's there basically by looking at it and seeing with our eyes and getting an idea of what the actual positions of those cars are that we're going to not run into and things like this. We might use a little bit of information from the fact that we have two eyes, and that allows us to know by comparing the images in each eye, we can see the parallax, the difference between if you cover one eye and then the other eye, you'll see that objects near to you seem to move as you look at them from your left eye, your right eye. Objects near to you will move more as you flip from eye to eye than objects far away from you. That phenomenon of parallax is the phenomenon that we use. We use part of that. We use that stereo vision to figure out how far away things are. By the time things are a large distance away, that's not how we do it. We typically do it just by what the things look like. And then we have a bunch of heuristics that we use to guess, oh, that thing is roughly such and such size, so therefore it must be this distance away. And sometimes we can fool ourselves, if there's the sort of fake person who's out there, who's very small, who's out there at a certain distance, we might think that they're further away than they actually are, because we kind of know, we think we know how big a person is, and it's not that size. Now, so the reconstruction of depth of how far away things are based on just what we see is something that we're used to doing. We now have machine learning systems that do a somewhat reasonable job of taking an image, even a single image, not even two images, and saying, guess how far away the things in this image are. Clearly, you can tell some things about how far away things are, because, for example, one object will obstruct another object. So then the object in front is in front of the object it obstructs, things like that. So those are things that you can sort of implicitly use in a machine learning system although you don't explicitly put in those rules in a modern neural net-based machine learning system, you just learn from a bunch of examples how far away things are. So there are different ways of figuring out how far away things are. A way that's used sort of nearby is to paint a pattern of infrared light that is just in a grid. And for example, a typical phone that's trying to recognize your face will do that. It will paint a pattern of infrared light on your face. And depending if it's like putting graph paper on something. So you have this graph paper and it's all marked off. If the graph paper is flat, then if you imagine projecting the pattern of crossing lines that's on the graph paper, you project it on something that's flat, the lines will all just cross at right angles. It'll all be exactly the way you'd expect on graph paper. But imagine you project it onto something that's curved, then the lines will have different forms and they won't anymore cross at right angles and things like this. And for nearby, that's a good way to figure out the shapes of things. Further away, a similar approach is LIDAR, laser, oh my gosh, what does it stand for? It's kind of the analog of radar with infrared light, where you're essentially having something that, a typical LIDAR device, even on a car, you're spinning something around and you're sending out light in a particular direction, and you're seeing, for example, how long it takes to come back, and you're figuring out from as it's reflected from an object, and you're figuring out from that how far away the object must be. So it's a much more direct way to work out how far away things are from you, rather than just looking at a picture and deducing, oh, well, I'm more or less used to the fact that, oh, that's a such and such kind of car, and I know they're really this big, so if they are that size in my image, they must be this distance away, and so on. In LIDAR, you're getting a much more direct, kind of precise map of the whole three-dimensional structure. And so what's the trade-off between these things? I don't really know. I mean, I think that what tends to happen is, look, the realistic fact is this will be done with image-based systems, because unless the hardware of LIDAR becomes simple and cheap enough that it's really possible to put a little bobble on the top of your car, not one of these giant things on top of your car, to do the kind of the LIDAR, to have a spinning thing with your LIDAR and so on. Unless somebody figures out how to avoid that, it's just going to be so much easier to just say, install some cameras and then do machine learning type techniques to figure out how far away things are. I think that this question of, can you fool? So LIDAR is very, very hard to fool, I think. Image-based things, they can be fooled by different kinds of things going on. They could be fooled, I don't know, somebody might have a painting of a car on the side of a giant truck that might confuse an image-based system. There are things like that. They're harder to fool, but realistically, they're going to be a lot cheaper, I suspect, unless some innovations happen in the hardware of LIDAR. And so my guess is that that's the direction things will end up going. I mean, I think the problem of self-driving cars is not so much this problem of sort of situational awareness, although that is one of the issues, but a lot of problems like, I don't know, making decisions about merging into traffic and, what are you going to do? And when do you take the risk of that other car may do a goofy thing? There's obviously a lot of degrees of freedom here because, for example, when a lot of cars on a road are self-driving and can communicate with each other, you can do completely different things than what you do if you have one self-driving car in an ocean of cars driven by those pesky humans who might do crazy things. So, and I think one of the issues is, when you drive, talking to people who do, for example, quality assurance for self-driving cars, you ask, what are some weird situations that tests of self-driving cars get into? They're driving along the road and suddenly, some weird kind of animal or a pack of animals walk into the road and start doing weird things. And the car's never seen that before, or it sees some weird kind of device that goes into the road and it doesn't know whether that's actually a bird that's just flying across the road or whether it's something else. So, there's a lot of weird situations that humans manage to say, hey, what's going on? I can decide what to do. And it's much harder to do something sensible in those cases. So I think the problems are not so much the detailed mapping, although it seems to help a lot. I mean, people are very concerned about very detailed mapping of roads and figuring out, at this point, you can do exactly this on this road, and we know exactly how this road is configured, so you can exactly move this way and that way, and it's all going to be okay. All right, maybe, let's see. See if there's one more I can try and do that is fairly short. I'll try and do one more. It's a question from Geek. What are finite fields and why are they important? So this is not about agriculture, it's about mathematics. What is a finite field? So normally we can think of numbers like integers, and there are an infinite number of them, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. We just keep counting forever. But there's a form of arithmetic where we say, imagine it's like numbers written around a clock face. They only go up to 12 and then they wrap back around to 1. That's so-called modular arithmetic. So if you take arithmetic mod 3, for example, and you say you've got 2 mod 3, you add 1 to that, you go back to 0. You add another 1, you go to 1. And you keep on kind of circulating around. You always are just 0, 1, 2. Those are the only numbers you can have. And when you add to those numbers, you're always just wrapping around. You're kind of wrapping around the circle of 3 numbers. Okay, so that's an example of modular arithmetic. Okay, so one of the questions about this is, if you do modular arithmetic and you do multiplication as well as addition, with addition, you can just, you add, and you might wrap around. And if you subtract again, you'll wrap back around the other way and all will be good. And in particular, every number will have an inverse under addition. So for example, you might have said, to reverse the effect of adding 1, when you're doing arithmetic mod 3, you would say, let's add -1. but you don't have a -1, arithmetic mod 3. You only have the numbers 0, 1, and 2. But if you work it out, adding 2 is the equivalent of subtracting 1, mod 3. So you can say that the inverse of 1, the inverse of the adding 1 is adding 2. So you have this notion of inverses. And let's see. So then the question is, what happens for multiplication? And it turns out that what happens is when you're doing things mod a prime, if the number is like 2 or 3 or 5, but not 4, not a number that can be broken down as 2 times 2 or something. Oh, actually, I'm about to get myself in trouble here. Yeah, there's a little trickiness about powers of primes. But let's start off with just primes. Okay, so modular arithmetic mod a prime has the feature that not only are there inverses to addition, there are also inverses to multiplication. And that gives you a certain kind of thing called a finite field that is a kind of nicely behaved mathematical construct. Okay, what are finite fields good for? They're useful because they're useful because they have this inverse property. But in particular, I'll give you an example of a place they're used. Let's think how to describe this. Okay, so if you look at the back of a book, physical book. I have a physical book here. Let's see, I've got a physical book here. Here's a physical book. On the back of the book is a barcode, okay? And that barcode has a number. It says ISBN, blah, 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 blah. ISBN, usually it starts with a digit. That ISBN is the International Standard Book Number. It's a way of saying every book that is registered gets an ISBN number. And that ISBN number encodes the country it's published in, the publisher, et cetera, et cetera, et cetera. Okay, those ISBN numbers, somebody had the bright idea when ISBN numbers were first made up, let's make sure that they have a check digit in them. That is, if somebody reads you an ISBN number over the phone and one of the digits is wrong, you should be able to tell that one of the digits is wrong without having to say, oh, can you repeat that number? Okay, so ISBN numbers have a check digit at the end. The last digit is a check digit. And one of the things you notice is that usually the numbers are just 0 through 9, et cetera, et cetera, et cetera. But actually, the last digit can sometimes be an X. And that's a little piece of finite fieldism poking its head out. Because what happens is the way those check digits are computed is using finite field arithmetic. And there isn't a finite field with size 10, which would give you just 10 possible digits, but there is one with size 11. So that X, because 11 is a prime, so that X shows up there because it represents the number 10, so to speak, that appears in the finite field of order 11, the field GF11. So that's, I'm not kind of really explaining how finite fields are used to produce those check digits, but roughly it makes use of the fact that there are these inverses and things to make, well, this would take me a little bit longer to explain. But basically, so error correcting codes is one place where finite fields are used a whole bunch. Those seep into a lot of different kinds of areas to do with sphere packing and all sorts of things like that. And there's lots of fun to be had with finite fields. It's much easier to describe them if I was actually showing on a computer and working with Wolfram language, where we can deal with finite fields in very nice ways, and actually seeing some of the things that happen. But that's at least some rough idea of what a finite field is, and at least one use for finite fields. All right. I think we should, well, let's see, do I get one more? You guys ask such interesting questions. I feel like I can go on, and I, the thing to realize is that as I answer these questions, they really help me understand the things I'm talking about more clearly. And I don't think I've probably ever given a long description of how fluid turbulence works, sort of off the cuff like that before. It's really, it's useful to me to kind of try and organize those thoughts in this way. So I appreciate that. But I think we should probably wrap up for now here. And I hope to be back next week. I will be traveling next week, but I think I'll be able to do this. We'll see, might be a different venue, might be more exotic, but I hope to be able to do this again same time next week. So thanks very much.